This is the second in a series of tapes on the subject matter of calculus. The material in these 8 tapes consists of the material normally found in a second semester course in calculus. This will be followed by a series of tapes on calculus 3. While different universities teach calculus from different books which are arranged slightly differently, the material in all of the tapes is presumably that which would normally be found in a 3-semester course in calculus, or a quarterly course in calculus. We're going to begin with subject matter of exponents, and in general, the section number on the tape number and the section number will be found up here, and the title of the tape here. Okay, I want to begin with a very basic idea of exponents, that which might be found in a course, perhaps even in grade school or high school. That's to say, for example, 2 to the 1 power is going to mean the number 2. And 2 to the 0 power, the number 1. And 2 squared, 4. And 2 to the n power will mean 2 times 2 times 2, using 2 as an example here, times 2, n times. One can then go on to divide 2 to any rational number power, to the p over q power, to be the qth root of 2 to the p. Or, what's the same thing, the qth root of 2 to the pth power. When one does this, you find that you can graph, for example, 2 to the x as follows. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared, or 2 to the 2, is 4. 2 to the minus 1. All right. Yes, we should mention here for negative exponents, 2 to the minus n is 1 over 2 to the n. That actually follows from 2 to the p over q. Well, providing we understand that this to the pth power means, so 2 to the minus p over q, for example, means 1 over 2 to the p over q. Okay, with this in mind then, 2 to the minus 1 is 1/2. It's 1 over 2. 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8. 2 to the minus 4 is 1/16. And you can see sort of a progression here. If you fill this in with all the rational numbers, you find that, for example, 2 to the 1/2 is square root of 2. That's to say 1.4, 1/4, and so forth. You fill this in here, and you find that you've got what looks like something that could be connected with a curve. Even though at this point you can only talk about taking 2 to a rational number power. We're eventually going to want to be able to take a number a bigger than 0 to any real number power, not just a rational number power. At any rate, this is the graph of 2 to the x for x rational. Right. For any a greater than 0, we want to be able to talk about a to the x. And at this point, we can do this for rational numbers x. For example, 10 to the x is going to look like this. It's 1 at 0, and it's 10 at 1, and it goes up faster than 2 to the x. Right? And then over here at minus 1, it's 1/10. And so 10 to the x looks like this. Ready? 1/2 to the x is going to look like this. It's going to look like what you would get if you flipped the graph of 2 to the x about the y-axis. It's going to look like this. So that, for example, a half to the 1 power is a half squared is a quarter, half to the 3rd power is an eighth, and so forth. So here's a half to the x. And I guess if we can include 1 to the x here, it's going to look like this. So for a greater than 0, we want to define the function f of x equals a to the x. And right now, all we can do this for is x a rational number. However, it's really clear, if you plot some of this, that you ought to be able to do this for real numbers x also, because the graph that you end up with when you plot it is very continuous here, so to speak, on the rational numbers. Okay, now, if we look at a to the x, for rational number x, there will be several rules. The rules of the laws of exponents. And you may check this. Maybe it pays to do so if you haven't looked at it recently, that this holds for exponents here when you have a to the x for any number a greater than 0. Namely, that a to the b times a to the c is equal to a to the b plus c. And a to the b to the c is equal to a to the b times c. And a to the b divided by a to the c is equal to a to the b minus c. And also that a to the 0 power is 1, and a to the 1 power is always equal to a. So here are laws of exponents for all exponents which are rational numbers and any real number greater than 0. Now I want to take a look at the subject matter of inverse functions with the idea of finding the inverse of the exponential function, which will be called a logarithm function. If f of x, all right, is 1 to 1, that is, if for each y, there is at most 1x, so that f of x equals y. Then we can talk about the inverse of function f, and that's written f to the minus 1 of x. And f to the minus 1 of x is going to be equal to y if f of y equals x. In particular, if a function f is increasing strictly or decreasing, then it's going to have an inverse. It's going to be 1 to 1, because if x1 is less than x2, then f of x1 will be less than f of x2 in the case where it's increasing. And a similar situation holds with decreasing. Okay. Now, what happens here is the following. If we've got a point A here, and f of A is B, this point then is on the graph. Well, this point here. And if this is the point B down here, and this, let's say, is the point A over here, then we can complete this type of picture here. Complete this, making a square here in the middle. This is going to be the point A, B, right here. This is going to, over here is going to be the point B, B. Up here is going to be the point BA. And here is the point AA. And so if AB is on the graph of F, then the point BA is on the graph of the inverse. Because if F takes A to B, then the inverse function is going to take B to A. So you can see from this that if you draw the line y equals x in here, right, you can get the graph of the inverse function by just simply flipping the graph of the function f. Perhaps f looks like this. Flipping it about the line y equals x. So it's going to produce a function that looks something like this for this particular f of x. Right. If the function f is continuous and increasing, then the function f inverse will be continuous and increasing. Or if it's continuous and decreasing, then the function f inverse will be continuous and decreasing. One can, for example, if this was f decreasing, then this would be the inverse function right here. Which is just what you'd get. So if this was g, for example, then this would be g inverse. Right. There's a further thing that you can note here, and that is that if f has a tangent or derivative, then it's reasonably clear from the picture, although the proof is a little bit complicated, that f inverse is going to have a derivative. And if this slope over here was m, so this, for example, would be 1 unit, and that would be m units, then over here, you're going to have a similar situation. This is going to be m, and this will be 1. And so that if f prime at a point x naught is equal to m, and y naught is f of x naught, then the derivative of the inverse function at y naught will be 1 over the derivative of the function at x dot. See, if this was slope m, then this is going to be slope 1 over m. And the similar situation holds here if m happens to be negative. Right? So that if you know the derivative of a function, and you know that it's 1 to 1, and let's say increasing or decreasing, then you can find easily the derivative of the inverse function. Right? There's a couple of other ways to do this, and perhaps this becomes a little bit more clear in the different notation. Using Leibniz notation, if y is a function of x, then x is a function of y when it has an inverse, and this would be the notation for the derivative of x with respect to y. And it's always understood that this is at the point x. And this says that the derivative of x with respect to y, where x is the inverse function of y, is 1 over the derivative of y with respect to x. Another way that we can get this same calculation here is as follows. If we know that f has an inverse, then we can write f inverse of x equals x. It's also true that f inverse of f of x equals x. That's to say, f inverse undoes what f does. All right? Now, if we take this right here and differentiate both sides of this equation, and we know that f has a derivative, then on the right-hand side, we get the derivative of x is 1. On the left-hand side, we get that the derivative, this is a composition, so that the derivative is the derivative of f at f inverse times the derivative of f inverse at x. And now we can solve this for the derivative of f inverse and get the derivative of f inverse at x is 1 over the derivative of f at f inverse of x. Now this looks a little clumsy perhaps, but when you do this with specific functions, it's not so clumsy at all, and this gives you a formula for the derivative of the inverse given the function. Right? We mention one more thing, and that is that several functions have natural inverses that you can solve for. It's not going to be the case for the inverse of the exponential function, but sometimes you can solve for the inverse function just by going about it and finding what it is. So that, for example, if y was equal to f of x was x plus 3, then if we solve this for x and find out, given a value x, if we solve this for x and find out, given a value y, what number x corresponds to that value y, we will have the inverse function. So that we get, for example, let me make this 2x plus 3 to make it a little more complicated here. We get that then x is equals to y minus 3 over 2, or the inverse function, f inverse of y, or f inverse of x, is going to be x minus 3 over 2. So for the original function, if you got the value y, by taking 2 times x and adding 3, to undo this, you want to take a number and subtract 3 and divide by 2. So you get an inverse function like so. Other inverse functions are also familiar. If f of x equals x cubed, then the inverse function is going to be the cube root of x, or x to the 1/3 power. So there are some situations where you can go about finding the inverse by simply solving for x in terms of y. When you can do that, then you can find the inverse to the given function. We now want to take a look at the subject matter of logarithms from an elementary standpoint. Recall we have the function a to the x. I'll draw this for a to the x for a greater than 1. And it's going to look something like this. We have these functions that look like this for rational numbers x. Right? Now, assuming that we can connect this right here, or even if we couldn't, we certainly have this defined for rational numbers x, so that what we could do is we could talk about the inverse of this function. And it's going to be what you get if you flip this about the line y equals x. It's going to look something like this. And this is denoted by the log to the base a of x. It's the inverse of the function f of x is a to the x. So this is f inverse. It looks something like this. Now, logarithms were originally used for a number of computations, and And that was their original value until it turned out that they've got considerably more theoretical value besides that. Logarithms obey several rules. So rules are laws of logarithms. All right. The log to the base a of b times c is equal to the log to the base a of b plus the log to the base a of c. The log to the base a of b to the r power is equal to r times the log to the base a of b, where r is a rational number. Right? And the log to the base a of b, this is an important rule for, these are computational rules. This is an important rule for changing from one base to another. This is equal to the log to the base c of b divided by the log to the base a of b. That's easy to remember here because you put log to the base c of a. And that's easy to remember because you put the b in the numerator and the a in the denominator. It's sort of the same relationship that you have here with the b above and the a below. To change to a new base c, or to compute in a base a when you know a base c, for example, log to the base 10 is commonly used. If you wanted instead log to the base 3 of a number, you can compute the log to the base 10 of the number and divide that by the log to the base 10 of 3. Right. Then in addition to this, log to the base a of 1 is 0, and log to the base a of a is 1. Right. You can think of this, the logarithm as a question. What power should you raise h to get this number a? And the answer is 1. What power should you raise h to get 1? The answer is 0. Right. These laws for logarithms follow from the laws for exponents. And let's take a look at how this occurs. Let's take a look at this right here, for example. To see that this holds, let's let u be equal to log to the base a of b. Right? Then that means that a is the power to the power u is equal to b. Right? Log to the base a of b is the power you raise 8 to get b. So a to the u is b. Let's let v be equal to the log to the base a of c. Then a to the v is equal to c. Right? So that b times c, multiplying these two equations together here, is a to the u times a to the v, which is a to the u plus v from the rules for exponents. And this says that b times c, the logarithm of it is going to be u plus v. That's to say, the logarithm to the base a of b times c is going to be equal to u plus v. And that's exactly what we want up here, right, like so. So that if u is log to the base a of b and v is log to the base a of c, then log to the base a of b times c is u plus v. That's to say it's the log to the base a of b plus the log to the base a of c. Let's check this one right here. Right. Let's let u be equal to log to the base a of b. That's to say, a to the u is equal to b. Right? And consequently what? B to the r power is a to the u to the r power, which is a to the u times r. So from this it follows that the log to the base a of b to the r is u times r. Of b to the r is u times r. And that's just exactly what we want, because u times r is r times the log to the base a of b, and this says that the log to the base a of b to the r then is equal to log to the base a of b times r. This one right here. Oh, to see that this holds, and this is a very important one here, because it allows you to change from one base to another. Let's take a look at what's involved here. Let's let u be again equal to log to the base a of b. And let's let v be equal to log to the base c of b. And let's let w equal log to the base c of a. And what do we have? We have a to the u is b, and c to the v is b, and c to the w is a. Right. So from a to the u equals b, from a to the u equals b, c to the v is b, and c to the w is a, we get c to the w is a, so that c to the w to the u, which is c to the w times u, is equal to a to the u. Right? C to the w is a, and a to the u is b, so that this is equal to b. All right? That's to say, well, that's not quite all I want here. Okay, let's let u equal log to the base a of b, v equal log to the base c of b, and w equal log to the base c of a. Right? Then a to the u is b, c to the v is b, and c to the w is a. Right? So consequently, a to the u is b, c to the w is a, so that c to the w to the u is a to the u, which is b. Okay, yes, this is it. So consequently we have the log to the base c of b is equal to w times u. And w is the log to the base c of a, and u is log to the base a of b. So this is log to the base, w c of a times the log to the base a of b. Right? So this says then that the log to the base c of b is the log to the base c of a times the log to the base a of b, and gives us the third result. What we're going to do now is we're going to take a different approach to logarithms and exponents. And this approach was developed, well, it was known, but it was developed for use in calculus books in probably the mid-1960s, about then. And the idea is, instead of starting with exponents, to turn the picture around and start with logarithms. This gives a development which allows you to not have to deal with the problem of defining exponents to real number powers where the real number is not a rational number. And it consists of the following. You define what's called the natural logarithm. And we'll see eventually here that it actually is a logarithm. Right? The symbol for this is ln of x. And it's defined to be equal to the integral from 1 to x of the function 1 over t dt. So that if this down here, let's say, is the function 1 over t, this is for t bigger than 0, a y-axis, let's say, and a t-axis. And here, let's say, is 1. Then, to get the natural logarithm, what we do is we integrate from 1 to x, this function, and this gives you the value of the logarithm. So then, in particular, we'll see immediately that this actually looks like a logarithm. At 1, the integral from 1 to 1 is 0. So we immediately get that the logarithm of 1 is equal to 0. Right? And then as you proceed in this direction here, to the right of 1, the logarithm gets larger. I'm going to draw it like this because I know pretty much what it looks like. It looks something like this. And when you integrate from 1 to x when x is less than 1, then you're going to get a negative number because you're going in the opposite direction. And so the natural logarithm is going to look like this. Right. Now, starting this way has the following benefits. The natural logarithm of x is defined for all x greater than 0. Immediately. You don't have to concern yourself at all with whether or not it makes sense to talk about the logarithm. Right? Also, the natural logarithm of x is continuous. This follows from the fundamental theorem of calculus, that ln of x is continuous. And also from the fundamental theorem of calculus, we have that the derivative of the logarithm of x, we know it immediately. It's 1 over x. And the fundamental theorems of calculus says this, right? That if f of x is equal to the integral from a to x, little f of t dt, and little f is continuous, then the derivative of capital F at each point x in the domain is little f of x. So if it's continuous on AB, then This is this. The derivative of capital F is little f. So consequently, what we have here is that the derivative of logarithm of x, we know immediately is 1 over x. And since 1 over x is going to be greater than 0, this gives us that ln of x is increasing. Right. The second derivative of the logarithm is going to be the derivative of 1 over x, which is minus 1 over x squared. X to the minus 1, the derivative is minus 1x to the minus 2. So this implies, since minus 1 over x squared for x greater than 0 is negative, this implies that ln of x is concave down. So I've drawn it like this. Right. Now we want to see a couple of other things about ln of x. We want to see, on the one hand, that ln of x, as x gets large, ln of x approaches infinity. We want to see that the limit as x approaches infinity of ln of x is infinity. To do that, consider the integral. This is equal to the integral from 1 to x of ln x is of 1 over t dt. Right? And so this is going to be larger than the integral if we just go to some number n of 1 over t dt. Well, let's look at what happens when we go to n. If x is larger than n, this is going to be larger than this. And what happens if we go to some number n? Well, if we look over here, and we go over to the number 2, we find out that there's a box of size 1/2 in here. Right, at 2. If we go over to 3, we can put a box of size 1/3 in here. And 4, 1/4, and so forth here. And so that this integral from 1 to n is going to be larger than 1/2 plus 1/3 plus 1/4 plus, I'm going to consider n to be larger, so I'm going to put a few more terms in here, 1/5 plus all the way to 1/8 plus 1/9 all the way to 1/16 plus, and so forth here, maybe up to 1/32 or what have you. And then what I want to do is note this. This first term here is 1/2. And these next two terms here, 1/3 plus 1/4, is larger than 1/2. Because there's two terms, they're each at least 1/4. Then there's 4 terms here, if we group these together, whose sum is more than 4/8, or 1/2. If we group a 9th to a 16th together, we get another 1/2. So we get that this is larger than 1/2, plus 1/2, plus 1/2, plus 1/2, and we can go out as far as we wish here, and we see then that this is the case. The limit as x approaches infinity is going to be larger than any number like so, which is any number of halves, and so the limit is going to be infinity. As soon as x is larger than some number n here, then this sum is going to be as large as we wish. So the limit as x approaches infinity of ln of x is equal to infinity. We're also going to want to see that as x approaches 0 from the right, the limit is minus infinity. But anyway, here are some initial properties of this natural logarithm function defined like so. And the reason perhaps why it's natural is the division 1 over t is a natural thing to do. Okay, we next want to see that this function ln of x behaves like a logarithm. And we want to show that, in particular, that the ln of a times b is the ln of a times plus the ln of b. So, first of all, let's look at ln of a times b. This is equal to the integral from 1 to a times b of 1 over t dt. And now I can write this as the integral from 1 to a of 1 over t d to t plus the integral from a to a times b of 1 over t dt. So what's left here then is to show that this is equal to the ln of b. Because what we have here now is this is ln of a. And now what I want to do is I want to make a change of variables in here. I want to let, see this goes from when t is equal to a to when t is equal to a times b. So I want to let u be equal to, let's say, t over a. All right? And then du is equal to 1 over a dt. And I can then make this change of variables in here. And consequently, when t is equal to a, so I get plus the integral. When t is equal to a, u is equal to 1. So this is u equals 1. When t is equal to 8 times b, u is equal to b. Right? And now I have 1 over t is 1 over 8 times u, and dt is a du. So I've completed the substitution here, so I have this all in terms of u, and now the a's cancel here, and I get that this is equal to the integral from u equals 1 to u equals b of 1 over u du, right? Well, this is the same as the integral. See, the u here is what's sometimes called a dummy variable. That's to say, the integral from 1 to b with respect to u of this is the same as the integral from 1 to b of 1 over t dt. So this plus ln of a. And so we get then that this is equal to ln of a plus this is ln of b. And we consequently have that the ln from natural logarithm of a times b is the natural logarithm of a plus the natural logarithm of b. So we see that the natural logarithm is beginning to behave just like a logarithm. We now want to consider a second property that logarithms have, namely that logarithm of a to the r is r times logarithm of a. We want to show that that holds true here for r, the natural logarithm. R ln of a for r, a rational number. Okay? And we'll use the over and over again the property here that the logarithm of a times b is the logarithm of a plus the logarithm of b in order to get this. Right? And also we know that the logarithm of 1 is 0. So we already have these two properties. We want this one right here. Okay? So first of all, let's note that the logarithm of a to the 0 is equal to the logarithm of 1, which is 0, and so that this is equals to 0 times the logarithm of a. And so the logarithm of a to the 0 is 0 times the logarithm of a. Likewise, the logarithm of a to the 1 is the logarithm of a, which of course is equal to 1 times the logarithm of a. So this is true for 0, and it's also true for 1. Let's look at it for 2. The logarithm of a squared is going to be equal to the logarithm of a times a, which according to this is equal to the logarithm of a plus the logarithm of a, or 2 logarithm of a. And that shows that it's true for 2. Logarithm of a squared is 2 times the logarithm of a. Okay? And now by induction here, for n, or for n plus 1. When it's true for n, it's going to be true for n plus 1. Because the logarithm of a to the n plus 1 will be equal to the logarithm of a to the n times a, which will be the logarithm of a to the n plus the logarithm of a. The logarithm of a to the n is n times the logarithm of a. So we're going to get another logarithm of a here. So this is n plus 1 logarithm of a. So it's true for, when it's true for n, we use that fact right here, or right here. All right, a logarithm of a to the n with n times the logarithm of a. It's going to be true for n plus 1, because we're going to get one more. So now it's true for all natural numbers. And 0. We now want to consider the logarithm of minus n, where n is a natural number. And this will then show that it's true. When we see that it's true there, then we'll find that it's true for all integers. Right? Well, the logarithm of a to the n times a to the minus n. Right? Well, a to the n times a to the minus n is a to the 0. And we know that the logarithm of a to the 0 is 0. But using this rule for logarithms here, the logarithm of a to the n times a to the minus n is the logarithm of a to the n plus the logarithm of a to the minus n. The logarithm of a to the n is n times the logarithm of a. And then this is going to be then, from this equation, this is going to be equal to the negative of logarithm of a to the minus n. Negative of log a to the minus n is going to be n log a, or log a to the minus n is going to be minus n log a. And so now we have this is true for all integers. Now let's consider irrational numbers. Of the form p over q, where p is an integer and q is a natural number. So we want all the rational numbers here, p over q, where p is an integer and q is a natural number. Let's look at the log of p over q times p over q times p over q, q times here. So times q. Right. Since there are q of these terms here, it's going to follow that this is equals to q times, I'm sorry, I want a to the p over q times q. I'm sorry, a to the p over q times a to the p over q, q times, so that there's going to be this to the qth power. Right? And now we know that this is q times the log of a to the p over q. Right? To the qth power here, it's q times the log of a to the p over q. And now, a to the p over q to the qth power, of course, is equals to a to the p. So this is the logarithm of a to the p also, right? Which is equals to, since this is true for integers, this is equals to p log a. So p log a is equal to q log of a to the p over q. And consequently, the log of a to the p over q is equals to, that's this, it's equal to p log a divided by q, or p over q natural log of a. And that shows then that this rule here holds for all rational numbers that form p over q. And it follows simply from this fact right here, and in fact the logarithm of 1 is 0. Those are the only real properties that we use in the logarithm. So any function that satisfies these two things here is going to satisfy the top one up here. In particular, our natural logarithm, the natural logarithm. All right, in a minute here we're going to want to look at the inverse of the natural logarithm function. To do that, we need one more property than natural logarithm function. We have already that the natural logarithm of 1 is 0, that the function is increasing and concave down, and the limit as x approaches infinity of ln of x is infinity, so that this goes and becomes as large as you want. We want to see now that the limit as x approaches 0 from the right of ln of x is minus infinity, so that this becomes closer and closer to the y-axis and gets more and more negative. And this is going to allow us then to talk about the exponential function. Well, what do we need to do here? If we consider the limit as x approaches 0 from the right of ln of x, right, we can change this around here and write this as the limit as x approaches infinity of ln of 1 over x, because as x gets very large, 1 over x gets close to 0 on the right. Right? But now this is going to be equal to the limit as x approaches infinity. From the rules of logarithms here now, this is the logarithm of 1, which is 0, minus the logarithm of x. So minus the logarithm of x is the limit as the logarithm of 1 over x. And now this is going to be equal to what? Minus the limit as x approaches infinity of log x, or minus infinity. So what this then says is that as x approaches 0 from the right, the logarithm function approaches minus infinity, and as it approaches infinity, the logarithm function approaches infinity. So what we have then is the following. The domain of the logarithm function is from 0 to infinity. The range of the logarithm function is from minus infinity to infinity. And it takes on all the values between minus infinity and infinity. So what we can then do is the following. We can look at the inverse of the logarithm function. The inverse of ln of x is going to be denoted by exp of x. We'll eventually show that it is an exponent. That's to say that there's a number e, and that this is going to be e to the x. Right? For the meanwhile, however, we can note the following. The domain of exponent of x is going to be from minus infinity to infinity, because the range of the logarithm function was from minus infinity to infinity, and the range of the exponent function is going to be from 0 to infinity. And just taking the logarithm function here, we also have exponent of 0 is equal to 1, and the function looks like this. Domain minus infinity to infinity, range 0 to infinity. Now, using the fact that this is the inverse of the logarithm function, we can find the derivative of the exponent function. Write, for example, logarithm of exponent of x is x. The logarithm and the exponent are inverse functions, so you get x back. Now differentiating both sides here, we get what on this side here? We get the derivative of the logarithm at exponent of x times exponent of x is equal to what? The derivative of the logarithm, of course, is 1 over x. So this is 1 over exponent of x times the derivative of exponent of x is equal to 1. Or the derivative of exponent of x is exponent of x. All right. So for the two functions here now, we automatically get the derivatives. The derivative of exponent of x is exponent of x. The derivative of the logarithm of x is 1 over x. Now, what does this say? Well, the exponent function is its own derivative, for one thing, but for another, the exponent is always positive. So the derivative is always positive, so we get exponent of x is increasing. Right? The second derivative of exponent is going to be exponent, which is going to be positive, and so since the second derivative is positive, the exponent of x is concave up. Right? We also get that the limit as x approaches minus infinity, the exponent of x is 0. Right? And the limit as x approaches infinity of exponent of x is infinity. This is growing in this fashion right here, and that can be just observed from the graph of the logarithm, for example. So we now have the exponent function. We've got its derivative automatically. It is its own derivative. It's an interesting fact on its own. And it's the inverse of the logarithm function. The derivative of the logarithm function is 1 over x. Okay, we now want to show that this exponent function actually is an exponent, and for that purpose we define the number e. E is the number so that natural logarithm of e equals 1. And here's your natural logarithm function. Right. Well, I didn't draw this very well. This is 1. This looks something more like this. The number e is going to be between 2 and 3. And in fact, e turns out to be equal to 2.71828188284. And this continues. It's not a rational number. Right? So e is going to be the number here, so that natural logarithm of e is equal to 1. And you can see this is ln of x. Since ln of x is the integral from 1 to x, of 1 over t dt, you can see here that, for example, if we go out here between 1 and 2, we're not going to quite get to 1 yet, because what? This is a box of size 1/2. We get about 3/4 here. If we go out to 3, however, and integrating from 1 to 3, you can compute here by approximation that this is going to be more than 1, and so consequently somewhere between 2 and 3 is going to be the number e. These two boxes are actually a half and a third, but if you add on here, you find that you get more than 1. The fact is that if you go up to 2.718 here, that's the place where the natural logarithm is equals to 1. Now, what we want to do is the following. We want to see that for rational numbers r, e to the r is exponent of r. And this is going to follow from our properties of logarithms. So that in particular here, e to the 0 is 1, and we know that exponent of 0 is 1. So e to the 0 is exponent of 0. Right? E to the 1 is exponent of 1. Now see, from the logarithm function here, the logarithm of e is 1, so the exponent of 1 is going to be equal to e. So we've got that this is true for 0 and 1. All right. What we want here is a rule to continue this. That's to say, what we want to do is to see that e to the exponent of a times exponent of b is equal to exponent of a times b. I'm sorry, a plus b. Well, this follows from the fact that logarithms behave accordingly. If we let u be equal to exponent of a, then we have the logarithm of u is equals to a. And if we let v be equal to exponent of b, then we have the logarithm of v is equal to b. And now, the logarithm of u times b is going to be equal to a plus b. And so from this we get that the exponent of a plus b is going to be u times b. Going backwards here. Logarithm of u times b is a plus b, so exponent of a plus b is u times v. That's to say the exponent of a plus b is exponent of a plus exponent of b. So this behaves like an exponent. Right? Having that, we can then get that this is true for n plus 1 when it's true for n. Right? Exponent of e to the n plus 1 is e to the n times e. Presumably, this, by induction, is going to be exponent of n times exponent of 1, which is going to be equal to exponent of n plus 1. So now we have this true for the 0 and the natural numbers. Exponent of n plus 1 is e to the n plus 1. All right, so we want to see now that it's true for negative integers. So we want to get it for the integers. So we want to look at e to the minus n. Right? This is 1 over e to the n, right? Which is equals to it's equal to 1 over exponent of n, but let's consider exponent of n. Consider exponent of n plus negative n. Right? This we know is equal to exponent of n times exponent of minus n, which we also know is equals to exponent of 0, which is 1. So that we have from this that exponent of minus n is 1 over exponent of n. And so that e to the minus n is exponent of minus n. E to the minus n is 1 over e to the n, 1 over exponent of n. But 1 over exponent of n is e to the exponent of minus n. So we get e to the minus n now is equals to exponent of minus n. We now have that this holds true for all the integers. It's now time to look at the rational numbers and determine that it holds true for the rational numbers. Well, consider numbers of the form p over q, right, where p is a natural number, where q is a natural number, and p is an integer. Exponent of p over q plus p over q plus p over q, q times here, right, is going to be from this exponent of p over q times p over q times p over q, q times. So exponent of p over q, add p over q together q times here, and you get this, and that's going to be equals to, from this fact right here, exponent of p over q times exponent of p over q times exponent of p over q, q times. So this is the case here. Okay. But this, right, exponent of p over q to the q power here is equals to exponent of p, right? P over q times q is p. Exponent of p now is e to the p. And from this then we get that exponent of p over q to the qth power is e to the p. So consequently, what? Exponent of p over q, exponent of p over q is equal to e to the p, the qth root of it, over q. E to the p over q, qth root of e to the p. And so this then gives us this right here. E to the rational number r is an exponent of r. Okay. Now what you want to do with this is use this. This says that for every rational number r, the exponent function agrees with e to the r power. So what we want to do is we want to define e to the x to be exponent of x. And then e to the x will be a continuous function that agrees with e to the r on the rational numbers and is continuous on all the real numbers. Right? So the question of how to extend exponents from the rational number to the real numbers becomes clear here. Namely, e to the x is the exponent of x. This is an exponent function for the rational numbers, and it makes then sense to extend it to the real numbers, extend the exponent function to the real numbers by defining e to the x to be exponent of x. Okay, we wish now to consider the logarithm of absolute value of a function f of x, and here's the reason for doing this. We know that the derivative of logarithm of x is 1 over x. This is for x greater than 0. What about x less than 0? Well, if x is less than 0, then we can consider the logarithm of minus x and take its derivative. Well, this is a composition. It's logarithm of minus x. So the derivative is going to be the derivative of logarithm, 1 over x, at minus x times the derivative of minus x. The derivative of logarithm of minus x is also 1 over x, now when x is less than 0. So we can put this fact together with the fact that the derivative is 1 over x when x is greater than 0, and note that the derivative of the logarithm of absolute x is 1 over x. All right? So we have here an extension, if you like, of the rule for the derivative of logarithm. Now, when x is 0, logarithm doesn't make any sense here, logarithm absolute x. But for all x's other than 0, derivative of log absolute x is 1 over x. All right? If we now consider the derivative of log absolute f of x, all right, this is going to be equals to the derivative of logarithm at f of x, which is 1 over f of x, times the derivative of f of x, f prime of x over f of x. Right? So it's worth remembering that the derivative of the logarithm of f of x, absolute f of x, is f prime of x over f of x. All right? From this we can also get an integral formula clearly. That's to say the integral of f prime of x, or antiderivative of f prime of x over f of x, with respect to x, is going to be log absolute f of x plus any constant. Okay? So, when you have got a combination that consists of a composition of logarithm and a function, you can differentiate it. For example, logarithm, let's say, of the sine of x, or absolute sine of x. The derivative is equals to the derivative of the logarithm at sine of x, which is 1 over sine of x, times the derivative of sine of x, cosine of x. So the derivative of log sine of x is f prime of x over f of x. That's to say, the derivative of sine over the sine. Right? The derivative of logarithm, absolute x squared plus 3x minus 7. And here you can include the absolute values. Frequently, for that matter, people write a parentheses and understand absolute values when they're using the logarithm. And you write the derivative of this is going to be 1 over the function times the derivative of the function. So 2x plus 3 over, x squared plus 3x minus 7. Similarly here, if you can recognize that you've got something of the form f prime of x over f of x, you can anti-differentiate. Right? So that, for example, the antiderivative of x over x squared plus 7 dx. Well, this is almost f prime of x over f of x. If we had a 2 up here, it would be. So if we put a 2 here and a half out here, we get that this is equal to 1/2 the log of x squared plus 7. Antiderivative, for example, here, of sine x over 3 plus cosine x. Right? Derivative of cosine is minus the sine. So the problem we have is this. Now we've got f prime of x over f of x. So the antiderivative is going to be the log, in this case minus the log of 3 plus cosine x. Absolute values here. And plus any constant in both cases here, of course. Okay. Back here, for example, if you've got the log absolute x minus 3 over x plus 7, and you want the derivative, here you can use the rules of logarithms here and write that this is equal to the logarithm of absolute x minus 3 minus the logarithm of absolute x plus 7. And this makes it easier to differentiate here using the rules of logarithms. So this is going to be equals to 1 over x minus 3. That's to say 1 over x minus 3 times the derivative of x minus 3, which is 1, minus 1 over x plus 7. Right? Similarly, if you had something like the logarithm of x plus 1 squared over x minus 5 cubed, say an absolute value, the derivative of this is going to be the derivative of 2 log absolute x plus 1 plus 3, I'm sorry, not plus, minus 3 log absolute x minus 5, which is going to then be equal to 2 over x plus 1. The derivative of x plus 1 is 1 over x plus 1 times 1, minus 3 times the derivative of log x minus 5, which is 1 over x minus 5. Right. Perhaps this would be more lustrous here if we had 2x minus 5 here, in which case there'd be a 2x minus 5 here, and then this would be 3 times 2 over 2x minus 5. That's the derivative of log 2x minus 5 being 1 over 2x minus 5 times the derivative of 2x minus 5, 2. All right, we know the derivative of the logarithm, and we know the derivative of the exponent. Derivative of the exponent of x is derivative of e to the x. We'll usually use e to the x. Is e to the x, huh? The derivative of e to the x is e to the x. Now, consequently, if we have something of the form e to the f of x, right, the derivative of this, e to the f of x, right, you have got to learn to treat as a composition. This is exponent of f of x. So the derivative is going to be exponent, the derivative of exponent, which is exponent at f of x, times the derivative of f at x. So say derivative of e to the f of x is equal to e to the f of x times the derivative of f at x. Right? So you could use, it's probably worthwhile knowing that, or considering the fact that over and over that exponent really, exponent of f of x is really a composition. It's exponent of f of x. You use that then to do some computations. For example, we had e to the sine x. We want the derivative of it. The derivative is going to be e to the sine x times the derivative of sine x. Right? E to the x cubed. The derivative of this is going to be e to the x cubed times the derivative of x cubed. And this has always been e to the x cubed power here. The derivative of x cubed is 3x squared. All right? Similarly here, e to the tangent of x. The derivative is going to be e to the tangent of x times the derivative of tangent of x, which is secant squared of x. Right? So e to the f of x, you get the first derivative, e to the f of x times the derivative of f of x. Conversely here, if you've got something of the form e to the f of x times f prime of x dx, and you want to integrate this you're going to get e to the f of x for the integral plus any constant. Now, you can obtain that by letting u equal f of x and du equal f prime of x dx. If it's not clear to you that you're dealing with something like that, you can, a substitution like this will get this for you. All right? Clearly, if u is f of x, then we're dealing with e to the u du, which is e to the f of x. It has e to the f of x for its derivative, e to the u for its derivative, antiderivative. Right? You can obtain that with this substitution. However, it's perhaps worth noting this, and when you see something that looks like it might be e to the f of x, f prime of x, you can get the antiderivative at a glance. So that, for example, if we had x squared e to the x cubed dx, we want an antiderivative of it. Well, this looks like e to the f of x times the derivative of f of x. If we had a 3 here, it would be. So if we put a 3 there, third outside, then this is, as for its antiderivative, 1/3 e to the x cubed plus any constant. And of course, you can always check antiderivatives by differentiating this and making sure that you get what you started with. That's the antiderivative of sine x, e to the cosine x. That's, well, the derivative of cosine x is minus the sine, so we put a minus sign here and here, and you can always put a constant inside the integral and correct by the reciprocal outside. Right? Because constant times the antiderivative of a function is the antiderivative of constant times the function. Huh? All right. At any rate, so that now this looks like f prime of x e to the f of x, and so that the antiderivative is going to be equal to, we've got a minus sign here, we have e to the cosine x plus any constant. And you can check that the derivative of e to the cosine x is e to the cosine x times the derivative of cosine x, which is sine x. All right, and we have got the derivative of cosine x is minus sine x, and we've got the minus sign here to correct for it. Okay. You can use this fact right here to differentiate things of the following form: f of x to the g of x power, where f of x is greater than 0. At any point where f of x is greater than 0. If you want the derivative of this, you could obtain it as follows. Write this as exponent of logarithm of f of x to the g of x. That's to say, e to the logarithm of f of x to the g of x power. And then this is going to be equal to e to the g of x log of f of x. And so the derivative is going to be equal to e to the g of x log f of x, which is f of x to the g of x. So it's going to be equal to this, times the derivative of the function that e is raised to. That's the derivative of e to the f of x is e to the f of x, f prime of x. So we take this again, which was f of x to the g of x, and now we need the derivative of g of x log f of x. But this is a product. So the derivative is going to be the first, g of x times the derivative of log f of x, which is f prime of x over f of x, plus the second, log f of x times the derivative of the first, g prime of x. Okay. Now, this is not a formula that's worth memorizing, but you can use this method here whenever you've got one function raised to another function power. For example, if you've got, let's say, x to the x plus 1 power, and you want the derivative of it, this is e to the x to the x to the log of x to the x plus 1, or to the x plus 1 log x. And so the derivative is going to be this, which is x to the x plus 1, times the derivative of x plus 1 log x, which is a product. So the derivative is equal to the first, x plus 1, times the derivative of log x, 1 over x, plus the second, log x, times the derivative of x plus 1, which is 1. So this is the derivative of x to the x plus 1 power. It looks like that. to the x plus 1 times x plus 1 times 1 over x plus log x. We're now going to look at what's called logarithmic differentiation, and it consists of the following. If y is equals to f of x, and we want to take the derivative of f, we can take the logarithm of y, actually the logarithm absolute y. This will be the logarithm absolute f of x. Now sometimes this can be worked with conveniently here and simplified if f of x lends itself to that. All right. Now, if we differentiate both sides here, we get 1 over y times the derivative of y with respect to x is equal to the log absolute f of x, the derivative of it, huh? And so we get that y, that multiplying both sides by y, we get dy dx is equal to y times the derivative of log absolute f of x. All right? When you've got a function to which logarithms apply, then sometimes this results in an easier way of computing the derivative. An example of when this can be done is something that we just looked at. For example, let's suppose we've got f of x to the g of x power. Let's say x to the x plus 1. Suppose this is f of x, or y. Then we take the logarithm of y, actually log absolute y, is equals to log absolute x to the x plus 1. Right? Using the rules of logarithms here, this is x plus 1 log absolute x. This is log absolute y. And now differentiating here, we get 1 over y dy dx is equals to, this is a product, so we've got the first as the derivative of the second, plus the second, log x, log absolute x times the derivative of the first. All right? So now multiplying both sides by y, we get dy dx, or f prime of x, is equals to this quantity, times the original function, x to the x plus 1. This can also work when the function is somewhat complicated and of the logarithm of it is simpler. So that, for example, suppose we have got y equals to, let's say x plus 1 to the 5th times 2x minus 3 cubed over 3x plus 4 to the 7th. Let's say even times e to the x. That's our y. Then what? The logarithm of y, the logarithm absolute y, is equals to 5 log absolute x plus 1 plus 3 log absolute 2x minus 3 minus 7 log 3x plus 4, using the rules of logarithms, minus the logarithm of e to the x, so minus x. And so what? If we differentiate the right-hand side here, we get 5 over x plus 1 plus 3 over 2x minus 3 times 2, log of 2x minus 3, the derivative is 1 over 2x minus 3 times 2, minus 7 over 3x plus 4 times 3 minus 1. So this is the quantity then 1 over y dy dx. So to get dy dx, we want to multiply this by y. And that's to say this quantity right here, x plus 1 to the 5th, 2x minus 3 cubed over 3x plus 4 to the 7th e to the x. That's going to give us then dy dx. It's this quantity right here. And it's clear that if this was arrived at then a lot easier than it would have been to consider this as either a quotient or a product, making these exponents negative. The derivative then of this quantity y, where f of x is y here, is the quantity right over here. Now you should be able to combine the logarithm and the exponent function with the other functions that you know, and you should always be able to differentiate anything because there are rules for differentiation. And a differentiation is a somewhat different story. It's going to take considerably more study because there aren't always rules for it, and sometimes it's not even possible. But let's take a look at some functions here. For example, if you have something like e to the 1 plus log x, and you want the derivative, this is exponent of 1 plus log x, so it's going to be e to the 1 plus log x times the derivative of 1 plus log x, which is 1 over x. If you have the logarithm of x squared plus cosine x cubed, the derivative of this is going to be 1 over x squared plus cosine x cubed times the derivative of x squared plus cosine x cubed, which is 2x, plus, well, minus the sine of x cubed times the derivative of x cubed, 3x squared. Any combination of things that you can put together here. The square root of e to the x plus log x. Remember, this is to the 1/2 power, so the derivative is going to be equal to 1/2 e to the x plus log x to the minus 1/2 times the derivative of e to the x plus log x, which is e to the x plus 1 over x. The derivative of tangent of log x is, the derivative of tangent is the secant squared, so this is secant squared of log x times 1 over x. The derivative of secant of e to the 3x. Well, this is secant of e to the 3x, and so consequently the derivative of secant is secant times tangent at e to the 3x times the derivative of e to the 3x. The derivative of e to the 3x is e to the 3x times the derivative of 3x. This is exponent of 3x. Derivative is e to the 3x times derivative of 3x, which is 3. Log 2x over sine x plus e to the cosine x. If you want the derivative of this, well, this is a quotient, So the derivative is the denominator, sine x plus e to the cosine x. The denominator and the derivative of the numerator. Logarithm of 2x as for its derivative, 1 over 2x times the derivative of 2x, which is 2. Minus the numerator times the derivative of the denominator. The derivative of sine x, of course, is cosine x. E to the cosine x has for its derivative e to the cosine x times the derivative of cosine x, which is to say times minus the sine x, all divided by the denominator squared. So sine x plus e to the cosine x quantity squared. Okay, so any algebraic combinations that you want here of these new functions with old ones, right, you can find a derivative of. Let's do one more. Oh, let's say e to the 3x plus log absolute x squared plus 1 to the 10th power. Right? The derivative is going to be 10 times this e to the 3x plus log absolute x squared plus 1. Well, that's 10 times it to the 9th times its derivative. E to the 3x, e to the 3x times 3. Derivative of log, so plus now the derivative of log of x squared plus 1, 1 over x squared plus 1, times derivative of x squared plus 1, 2x. So there's the derivative then of that.